Okay, these are the notes for 4.9, where we're going to hit the recursive and explicit rules for a geometric series, so we can talk about finding the sum of a geometric set of numbers. So yesterday was arithmetic, so generally speaking, your sequences were all ones that had a common difference. Again, we'll be using the idea of recursive to explicit rules and then use that explicit rule in the bigger sum formula so you can do a sum. And like yesterday, we'll have sums where you've only got to sum up maybe 5, 6 terms in the sequence. In that case, you write out the series. Remember, the series is the list of numbers, written at the list of terms written as addition, and then the sum is what you actually get when you add them. And then when that list gets to be longer, so let's say it's 50 terms or 100 terms, then like yesterday, we want a formula that will take care of that for us. So we've got a formula that will help shortcut all that work. So we'll kind of really repeat the notes for the most part that we did yesterday, a very similar approach. We're going to start with a little bit of review idea and actually something a little bit new thrown into the review. So we know from back in chapter 2 that when we do a recursive, we always start with the use of 0, or most of the time we start with the use of 0. And then use our rule, our recursive rule would read common ratio times the previous term. What we didn't do in chapter 2 is we never did really do an explicit rule that was geometric. We didn't hit that till the first half of this chapter when we started talking about an exponential function. Now, when it was exponential, we actually wrote it as a b to the x, and we did it as a function. So we said f of x is equal to. So what we're going to do here is we're going to go back to our kind of our standard recursive or just sequence type rules, not using this. So while that was true for the first half of chapter 4, we're going to go back to more of a typical look for this part of the chapter. So we're going to use u1, r, and then to the exponent n minus 1. This is unique to a sequence. This is unique to an exponential function. Slightly different than the way we talk about it. Okay, so let's do that and carry on that way. First of all, just like we did yesterday, we're going to just practice a little bit, using a recursive rule that's geometric. So our first term is 3, and the rule says 3 times the previous term. So if we start doing 3 times the previous term, we'll generate our terms. Remember, we can also go backwards. When you go backwards through the sequence, it would be division, so we'd be dividing by 3. Or you could think of the use of 0 as what times 3 would give you a 3, which would have to be a 1. So there's me just, again, practicing doing the rules doing the terms in a sequence. Now, if we go to explicit, and we're using this version of explicit, things we need to know are what are the first term, which we know is 3, what is the common ratio, which is also 3, and that we can tell by either looking at the recursive rule, or if we had the sequence list, we could just check out our terms and figure out our common ratio by looking. Now we go to fill it in as explicit, and it looks like this. So we've got first term, common ratio, just happen to be the same number, n minus 1. And then the idea here is what's the 20th term? Well, like we said yesterday, we don't want to list out 20 terms recursively one at a time, then go back and say, all right, well, I got my 20th term and there's my answer. We want to just be able to have a shortcut. Explicit rules are always a shortcut. They allow you to plug in the number you're trying to find. The term's position in the sequence is what you evaluate at. Now here when we go to plug in, your n's going to go in up here as an exponent. So we start out with 3 times 3 to the 20 minus 1, which is really 3 to the 19th. So if you want to write 19 here, that's fine, but at least in the notes we want to see where that's coming from. And then obviously do your calculator and a pretty good sized number. When you start doing things to exponents, especially exponent as large as this, and your base is a number bigger than 1, you're talking about a growth here, you're going to get a pretty good sized number. Okay. So 20th term in this sequence. So if you continue this sequence out till we got to the 20th term way out there, this would be the number that would sit in that spot. Okay, so apply it to the concepts from yesterday, which is partial sums. Remember, partial sum just means simply you're not looking at like an infinite list or maybe even a really long list. You're looking at a smaller set of numbers. So maybe the first 10, the first 20, whatever. And that's pretty typical. If you had a large set of data, and maybe it was a study that ran over several years, you might go, well, let's look at the first 6 months. Let's look at just the first year. Or if it's 10 years out, let's look at the first 5 years, the first half. And the idea of summing whatever it is you're looking at. So partial just means, we don't want to look at the whole thing. We want to look at just a snapshot of it. So again, practicing the idea of, let's just get some terms going. First term, 48. Our recursive rule says half of the previous term, multiplying it by half, or if you want to see dividing by 2, that's fine. So here's U1, half of that, half of that, half of that. Remember, when we're going to do the sum, we write what's called the series. As a reminder, I'm going to keep reminding you guys this a few times. This is what's known as the series. Sorry, I'm so sloppy. I'm writing with my mouse here. But the series is the list of terms with the addition between them. The sum is the actual answer. So here's a series, here's a sum. Same as it was yesterday. Now, if you do the partial sum idea, which again is pretty easy, and you got a list of terms, partial sum. So if we're doing the sum of the first 5 terms, which is what that says, you're going to add up the first 5, get your number. Sum of the first 4, so again, we're looking at just a snapshot of the overall sum of the first 3, and so on, like we did yesterday. And again, the idea being with the dot, dot, dot is this sequence goes on forever, and we're not looking at forever, we're looking at just some of it. Now, if we were going to do a recursive and an explicit formula off of this sequence, things we need to know recursively is how are we starting? Or excuse me, what are we doing? So we're going 3 times the previous term. First term being 2, the use of 0 term would actually be a fraction, but in this case, the way this reads, we start with U1, as our first term in the sequence. So the first term we're doing something to in the sequence, to be clear on that. So 3 times the previous term. When we go explicit, we need to know what is the first term, what is the common ratio. Well, the first term is clearly 2, and the common ratio is to multiply by 3. So when we plug in these values, we're going to look like that. Now, if I wanted to go further out in the sequence, what's like the 100th term? Plug in 100. What's the 50th term? Plug in 50 for my n. Go to my calculator. So again, the difference between recursive, r times the previous term, explicit, first term, and r. Again, it has more of an exponential look, so it does at least somewhat relate to that first part of the chapter. Well, then the idea is to build the sum idea the same way we built it in the set of notes on arithmetic. Is you got the summation notation, which is the symbol that says here's what you're going to do. And then when that sum gets bigger, more terms than 5 or 10 or whatever, use a formula. The formula will shortcut when we got long list of terms. This is not a particularly long list, right? 1 to 5 is 5 terms. Remember how that works? So if it was 1 to 5, count our fingers, 1, 2, 3, 4, 5, that really is 5. If it was 0 to 5, that would be 6 terms. And sometimes we give you a sum where we don't start at 1. When you do that, you got to really think carefully about how many terms would that be. So generating the terms would be as simple as you plug it in. So we start with 1. Now, in this case, when 1 goes in, it goes in as an exponent. So when you go to put that 1 in for the first problem, it's going to be here. Well, that's an exponent of 0. Anything to 0 power is 1, so your first term is 80. And then all of a sudden you plug in a 2. Okay, well then your first term is going to be, your exponent is going to be 1. 2 minus 1, 0.5 to the 1 is 1. So you're taking half of 80, which is 40, and so on. So the key here with with a geometric is that you're plugging in for the exponent. But first term, plug in a 1. Second term, plug in a 2. Third term, plug in a 3, and so on. So the sum of the first 5 terms, there they are, and 155 is your answer. So remember, this is the series, this is the sum. So very straightforward. Just like we did yesterday, same symbolism. You notice up here, it says k. K is like number of terms, often, so 1 to how many terms. U sub n is the rule that generates the terms. They're probably written like this. This is just the general symbol for it, but here's how we'll see it, just like it is down here. Let's try a few more before we wrap it up. Now, the explicit formula for the partial sum is that formula that helps you do the sum when you've got, for example, 30 terms instead of 5. If it was just 5, I probably would just go ahead and find the 5 terms, add them together, and call it a day. But with 30, I don't want to list out 30 terms, so I'm going to work off a formula. It's got the first term in it, the common ratio, and the number of terms you're going to sum. In this case, we're given the first term, obviously. There sits my r, and we're going to do the first 30 terms. So when I go to set it up, it looks like this. First term 60, 1 minus r to the whatever your number of terms is, exponents. In this case, 30 is my exponent. 1 minus r. Go to your calculator. This one comes out to be approximately 100. The thing about this one is that 0.4 to the 30th is an extremely small number. When you go to do the calculation of 1 minus 0.4 to the 30th, your calculator might just give you 1. And what it's trying to tell you is that 0.4 to the 30th is so small, basically it's like saying 1 minus 0. So it kind of does, your calculator will do a little bit of an approximation, and that's fine. Just go with it. Okay, well, let's put this into the form of a word problem. So you're getting hired to do a new job. Your starting salary is $32,000 a year. Each year for the next 10 years, you're guaranteed a 3.75% raise. Write an explicit formula, and then use it to basically answer some questions. So to do the explicit, a couple things we'd have to know is what's the use of 1, which would clearly be $32,000, my first year's salary. And what is the common ratio? Now, there's a thing here that would be easy for us to make a mistake. We've talked about this in the past, that if I'm getting a raise and I want to figure out the next year, you can't just take your salary times 3.75 or 0.0375, because all that'll do is give you the raise. It won't give you the new salary. So you guys remember these problems from the past. If you want to carry the $32,000 with you and get the raise tacked onto it, you got to throw a 1 in there as part of your common ratio. So when we go to set this up, here's what you're going to see. 32,000 is my first term, and again, all I'm doing is operating right off of this, so I'm just modeling this. My R is not 0.0375, it's 1.0375. 1 brings 32,000 with, 0.0375 brings my raise with, then it combines them as my overall number. So there's a explicit formula. Now I can go any year I want, 2 years out, 3 years out, 10 years out, and figure out my actual salary. So if we're going to do the 10th year, it'd be use of 10. So I plug in 10 as my exponent. So at 3.75 every year for 10 years, my 10th year, I'm making 44. Now when you want to do the sum of those 10 years, different question. So this is specifically in a certain year, what is going on in the 10th year? This is saying what is the total of my earnings over the course of those 10 years. You got to, and there's the word total in there too. You got to kind of identify the words that tell you what you're trying to do. So a specific year, a sum. So if it's a sum problem, I'd be working off of the sum formula. We know the first term is my starting salary. We know the common ratio. Plug it all in. 32,000, 1 minus, remember now my R is got the 1 point to the 10 years, 1 minus, everything in your calculator. One thing you guys do want to do, I guess, a little bit of it, or try to watch out for, excuse me, is being careful with how you do this on your calculator. Really, you'd probably want to do the number to the decimal first, then 1 minus that, then times 32,000, then divided by. And there's lots of errors to make in calculations, so you should really practice this on your calculator, making sure you're getting the same answers. Okay, so there's the sum of 10 years worth of salaries. Different than finding an individual year in those 10 years. All right, and that's the notes for geometric partial sums. 2 days I think flow pretty nice. It's all formula based. You're doing very similar stuff both days. And then when I return, we'll talk about both days homework at the same time. Good kind of comparison. The next thing I have you guys do is do a little quiz review. There's a video for that, so you can catch that stuff in the next video.